that we can use for these alleles would go something like this. CCR5 delta 32, and then the CCR5 plus. Anytime you see this plus, that indicates wild type, and the wild type is abbreviated as WT. Okay? All right, so let's go out into the population and let's look at these particular alleles. And what we're going to do is take everybody that we find, take some blood, and figure out what their genotype is. If there are only two alleles in the population, the delta 32 allele and the wild type allele, there should only be three genotypes. Two alleles, three genotypes. There would be a delta 32 allele, delta 32. This individual is homozygous delta 32. The slash here is notation that means that these two alleles are on different chromosomes. They should be on the two homologs, right? Yeah, they should be on homologous chromosomes, one from dad, one from mom. So the slash just means that that's homozygous delta 32. I could also have heterozygote, one delta 32 allele and one wild type allele. And then the last possibility is the wild type, that's the homozygous wild type. So I have three different genotypes. Now, what I'm going to do is take everybody's alleles, figure out what they are, and I'm going to dump them into a bucket. I find this a little bit easier as kind of a good analogy is to talk about this bucket of alleles. The bucket of alleles is basically the population of alleles. Right? If I take everyone's alleles, take copies of them by looking at blood, and I dump these into my bucket of alleles, I now have a bunch of alleles in the bucket, but I have no idea what the genotypes are that were used to generate that bucket of alleles. And in fact, in evolutionary biology, I really don't care. I just care about the bucket of alleles. I don't really care about the source of these alleles in terms of genotypes. I just care about the alleles in the bucket. There should be a bunch of delta 32 alleles and a bunch of wild type alleles floating around in this bucket. And what I'm interested in figuring out is the frequency of each of those two alleles in the population. So my notation here, f of delta 32, is the frequency of the delta 32 allele in that bucket of alleles or in the population at large. I could also talk about the frequency of the wild type, and my notation would be f of plus. Okay, I have the frequency of this allele and the frequency of the wild type allele. I can figure out these frequencies with some very basic math. I just need to know the number of delta 32 alleles in the bucket, and I need to know the total number of alleles in the bucket. To calculate the frequency of the wild type allele, I need to know the frequency of the wild type allele, and I need to divide that by the total number of alleles in the bucket. Is that okay? All right. Frequency of the delta 32 alleles and the frequency of the wild type allele are given by some very basic algebra. If the delta 32 allele and the plus allele are the only two alleles in the bucket, then it should be true that the delta 32 frequency plus the wild type frequency should sum to 1. If there's more than two alleles, that won't happen. But if there are two alleles in the bucket, the frequencies added together should equal 100%, because that's all the alleles in the bucket. Is that okay? All right. So let's do that. Let's go around the world collecting blood from individuals. Let's figure out their blood types, their CCR5 types, and dump those alleles into a big bucket and figure out the frequency of the delta 32 allele in each location around the world. Okay? All right? And I may have forgotten to mention this, but it does link back to HIV. Individuals that have delta 32 alleles are immune to HIV. There's something about the CCR5 receptor. It's a different shape if you're delta 32, which means it's harder for HIV to gain access to those CD4 cells. If you can't get access to the CD4 cells, the virus can't have itself copied. So these individuals are going to be immune to HIV. All right, in any event, in some parts of the world, like Africa, Southeast Asia, North America, South America, the frequency of this allele is so low it's almost non-existent. On the other hand, there are other parts of the world. Here, these would be, it's that Finland and the Baltic states, right? Latvia, Estonia. We're talking about frequencies closer to 14%. Here, less than 1 out of every 100 alleles is delta 32. Here, greater than 14 out of every 100 is the delta 32. Okay? So, this is kind of interesting from an evolutionary biologist standpoint, because we might want to ask some questions about why it is that the frequency of this delta 32 allele differs in frequency depending on where you are on the planet. Okay? Now, the reasons for this fall into 2 main categories. The first reason that this could be true has to do with a force that we've already talked about, and that's natural selection. The argument would go, well, if the delta 32 allele confers resistance to HIV, and there were lots more HIV up here than here, then natural selection would push for an increase in the delta 32 allele in those locations. Okay? That's a natural selection type argument. Well, natural selection is an evolutionary force, and it fits within a group of evolutionary forces that are referred to as the deterministic forces. Deterministic means it can be determined, it can be predicted. Natural selection is one of these deterministic forces. There are other evolutionary forces that, like natural selection, are deterministic. If you tell me what the frequency is now, you tell me something about the regime under which these forces are operating, and I can predict what the allele frequency will be at some point in the future. It's very easy to determine because these forces are working in a deterministic way. What we're going to do over the next couple of weeks is talk about natural selection again. Can't be avoided. We're going to have to talk about it again. And we're also going to list off some others that are also deterministic but work differently than natural selection. Okay? All right, now the fact that I've done this as 2, what does that suggest about these forces if they're not deterministic? So this group of forces is said to be stochastic, and stochastic is just a fancy word for random. The thing about these stochastic forces for evolution is you can't predict them. You know they're operating, but you really don't have any idea what the consequences on allele frequencies are going to be of these random forces. You can predict the effect of the deterministic forces. You cannot predict the effect of these stochastic forces. So over the next few weeks, as we tear apart these evolutionary forces, some of them are going to be deterministic. I will have equations that go along with them. And some of them are stochastic, meaning I don't know what's going to happen. Okay? All right. Let me just switch my PowerPoints over here. Okay. Switch my PowerPoints. And what I want to do is just go through here and show you how to take a population and pull out its allele frequencies. And that will be important for what we're going to be doing. So let's start here with the Ashkenazi European population. Number of people tested equals 43. And of those people, there were 3 genotypes. Homozygous wild type, heterozygous, homozygous delta 32. So, of the 43 people, 26 were homozygous wild type, 16 were heterozygous, and 1 was homozygous delta 32. So, what is the frequency of the delta 32 allele in this population? And what's the frequency of the wild type allele? Okay, you might want to stop the video at this point, see if you can work out an answer to the problem before I work it out. I think it'd be good for you to run through it because there are some common mistakes that are made by people. But if we think about this as a bucket of alleles, close to St. Patrick's Day, it's over, but bucket of alleles, bucket O alleles. If we talked about these 26 people and we took their alleles and put them into the bucket, how many alleles did they contribute? Well, each individual has 2 alleles, so that would be 52 alleles contributed to the bucket. Of the 52 contributed, they're all wild-type alleles. These individuals contributed 32 alleles, but their 32 alleles consisted of 16 wild-type and 16 delta 32 alleles. This last individual contributed 2 alleles, both of which were delta 32. 43 people contributing 86 alleles. So, of the alleles in the bucket, how many are delta 32s? Well, there's 16 contributed by the heterozygotes and 2 contributed by the delta 32s. I could draw this out for you. That'd be 16 plus 2 divided by the total, which is 86. This then would be 18 over 86. Okay? If we did a quick calculation here, 18 divided by 86, 20.9. Right, 20.9%, otherwise known as 0.209. Okay, the wild type, I would recommend whenever you do these calculations, you automatically do both. Then you have a way to check yourself at the end. If I do this right, what should the 2 frequencies sum to if there are only 2 alleles in the bucket? They should sum to 1. The natural temptation would be to say, okay, well, if I have this one, then this would just be 1 minus 0.209. The problem with doing that is if you just goofed up the math here, the math's going to be goofed up here. Whereas if you go ahead and do the calculation here, then you can test if they equal 1 or not. If they don't, you made a math mistake somewhere. Right? So the wild type here is going to be 52 plus 16 is 68 plus, no, that's all of them, right? That's, sorry, that's, I need a bigger board. 16 plus 52, right, over 86 again, total number of alleles in the bucket. This would equal 68 over 86. 68 divided by 86 equals 0.791, or 79.1%. 0.791 plus 0.209 sums to 1, so I'm pretty confident that my math is okay. All right, it could be close, right? Depending on rounding, it could be 0.999 or 1.001 or whatever, but if you're close to 1 at the end of this, you can feel pretty good that you did your math properly. Okay? Close this out. Go back to this. Okay? We could do the same thing for the next population. Just checking the time here. Do the next thing for the population. I tested 102 individuals. 75 were wild-type homozygous, 24 heterozygotes, and 3 homozygous delta 32s. That means there were 204 alleles because there were 102 people. Let's do wild-type first. There were 75 people contributing 2 alleles. That's 150 wild-type alleles plus 24 divided by 204 alleles. That would be 174 out of 204. And the frequency of the delta 32 is equal to 6 plus 24 over 204. That equals 30 out of 204. Once you do the math, I think what you'll come up with is 85.3